Okay, so this is meant to be a overview or introduction to our forces unit, chapter 4 from the textbook. This is not meant to supplement the reading notes that you should do for the reading notes quiz. Replace. This is not meant to replace those reading notes. This is meant to supplement it, though. Give you a little bit of additional background information, walk you through a few specific sort of things. Very few of the answers for that particular quiz are going to pop up here, but it is going to be a nice overview of the symbols we use, why we use those symbols. That way, when we start drawing these things together, especially when we get to our free body diagram stuff, that way when we start drawing these and working on these together, you understand what it is I'm writing, why I'm writing it, and at least have a location where you can come back and refresh yourselves on what symbols we use and why we use them. So that's what this first set of notes is all about. It's the symbols we're using and why we use them. So a force is going to be a push or a pull of any kind, right? That is straight from the chapter. That is straight from the textbook. I think it's even your first question on the reading notes quiz. Now, this is going to be a vector quantity. What we mean by a vector quantity is that it not only has a magnitude, a size of the amount of force, how much pushing or how much pulling is occurring, but it also includes direction. Right? Is it a push or is it a pull? Is it to the right, to the left, north, south, east, and west? How does that direction relate to other forces that might be acting on it, right? If two forces are working together, pushing in the same direction, then you would add those two vector quantities up. But if they're in opposite directions, one is positive, one is negative, and technically, while still adding them, right? If you add a negative, it becomes subtraction. So the direction is going to be a big factor here. Now, the metric system, SI, System des Internationale, the metric system units for force are going to be newtons. We named it after Isaac Newton, obviously. He didn't name them newtons himself. He did the pioneering work, so we gave him the name for the unit. 1 newton is basically a combination. It's an amalgamation of smaller fundamental units. You'll notice 3 fundamental units in this unit for a newton. You have kilograms, which are our new measurement or new way of quantifying mass, how much material is present. And then you still see meters as your measurement of distance, and time as your measurement of seconds. Seconds, your measurement of time. It's early, I still need more coffee, sorry. But you'll notice those 3. Now the other part you should notice too is that these units right here, meters per second squared, that is an acceleration. And our units for mass are a kilogram. And when you multiply them together, a newton is literally just, this is where our equation for force comes in, the one that you're probably familiar with from junior high or pop culture, whatever, F equals ma. This is where we get the units of newtons. It is a kilogram meter per second squared because units of kilogram are units of mass multiplied by units of acceleration, meters per second squared. And instead of every time we want to talk about how much force something exerted on something else, instead of saying, well, it was 50 kilogram meter per second squared, we just simply say it's 50 newtons. Significantly less of a mouthful, easier to quantify, right? So we still have these 3 basic units of measurement: mass, distance, time. But now we're getting into more complex units. And instead of describing it as a kilogram meter per second squared every time we want to talk about an amount of force being applied to an object, we simply rephrased it and called a kilogram meter per second squared a newton. That's all that means. Now, applied forces. Forces that 2 objects apply to one another typically come in the form of contact forces, right? So contact forces, or any applied force, or where 2 things are physically touching each other. This is different than our at a distance sort of forces. And we'll talk about what's happening with your at a distance sort of forces, like gravity and magnetism. They're not really at a distance, and it's kind of neat, but we have to get to gravity first. So any applied force, any push, any pull, anything that in general is going to be applied to an object to cause it to move or to change its state of motion, we're just going to label with an F and a subscript of an A. The capital letter F, meaning it is a force, just like we did with VI and VF as velocities, right? The subscript just defined what kind of velocity we were dealing with. In this case, that A is just going to define what kind of force we're describing. So this is any generic contact force causing an object to speed up. This could be a force of tension. I will always write it out as F sub T. right, instead of the capital letter T. I don't like to use that one because I use a capital letter T for something else, but if you're using outside resources, another YouTuber or a different textbook, maybe you've got a sibling taking college level physics courses, they might use the capital letter T as their tension. But I'll always use F with a subscript of a T just to keep the theme going of the capital letter. The big letter is what I'm measuring, and then the subscript, sorry for the bell, the subscript defines or clarifies what kind of force it is I'm looking for. We can also do this with friction, right? F with the subscript of another lowercase f is going to be our force of friction. That's the abbreviation I'm going to use for that one. And then the normal force. Yes, that is a force. Yes, it is a really lame name for naming a force, but it is a very, very important one that we're going to use. Would I have personally labeled it the normal force? No, I'd come up with a slightly different name for it. But I wasn't around 500 years ago when we came up with all of this cool stuff, so here we are. Again, F with the subscript of an N. I like to keep the theme of capital F's being my forces, and then the subscript just describing what that force is. And I'll continue that form the whole time, or that generic way of doing things the whole time. So tension, to be specific about what tension is any sort of force exerted by strings, ropes, cables, any of those sorts of objects. You can even have tension in steel beams and things like that. We'll talk about that if you take my engineering physics course next year. But tension is basically a pulling force, strings, ropes, and cables. Tension along the string is constant. So if you've got a tension or a force of tension that is applied right here where the rope is tied, and we want to label this as 10 newtons, then that means the force of tension here, here, and here, and here, all along it is still 10 newtons, right? This is 10, this is 10, this is 10. The force and tension along the rope is constant the entire way. Which is why if you have a weak spot, obviously the rope might give way and tear. But that is tension. That's all you really need to know about tension. Friction. Friction is going to be a big idea, especially in the second half of this set of material, this unit, I should say, for Unit 5. It's one of the main ideas, right? Friction acts to oppose any motion or any attempted motion, right? So friction can work on moving things to cause them to slow down. You take your foot off your gas pedal while you're driving your car, and your car will gradually begin to slow down from the air resistance as it tries to break through the Earth's atmosphere and move through the air in front of it. You've got friction between your tires and the road, friction in your axles and your gears, and all sorts of places where friction is occurring. But it can also prevent attempted motion if your car breaks down on the side of the road and you've got to try and get it moving out of the way. You need to get out of the car and begin pushing. You might push on the back of the car and it might not go anywhere. And that's friction working against you, right? You've got your two forms of friction, static friction versus kinetic friction. Static friction prevents stationary objects from beginning to move. It keeps you stationary. They start with the same root word, and that's the way I like to recall it, right? Static friction and stationary. They have the same root, and they mean the same thing. Kinetic friction is the friction that you get from things that are already moving. And it's the friction that will slowly begin to bring it to a stop. Air resistance or drag, typically something that we're going to ignore in most cases. If we're not ignoring it, I'm removing a lot of variables like the air density or temperature or humidity levels or the aerodynamic properties of the car as it drives through. I'll just give you a flat number for air resistance if I include it. I traditionally don't. So don't worry about having to do too many calculations with that. But it is something that you can include. It's not normally going to be a zero. And then the normal force. All right, I mentioned a moment ago that the normal force is a term I would have not given this force, but it is crucial. It is important. The normal force is the force that we attribute to keeping objects apart. If I want to put my chemistry hat back on real quick and go back to the good old days of teaching chem, honestly, it all comes down to intermolecular forces. Probably not your favorite portion of your chemistry class last year, but it was important nonetheless. These forces are exerted between the electrons in those molecules, and those electrons will always, always, always repel one another. So whether or not you're dealing with London dispersion forces, hydrogen bonding, dipole interactions, whatever the order of magnitude, of strength of those intermolecular forces were that you had, They are what is keeping you from falling through your chair right now. They are what is keeping you from your laptop from falling through your desk or your cell phone from falling through your hand. They are what keep things apart and repel one another. Now, you can apply enough force to overcome and overwhelm the normal force, right? It happens all the time. Chairs break, people put their hands through a wall, whatever it might be. You can apply enough force to overwhelm the intermolecular forces holding those molecules together, but it takes quite a bit, right? The normal force is basically the object pushing back against you, trying to prevent you from occupying the same space as the material that it was already occupying, right? You push against the wall pushes back, you push against the floor pushes back, all of those sorts of things. So those are your contact forces. Action at a distance forces are the things that you can experience and feel without having contact being a requirement, right? There is no contact between these, not necessarily. There is some contact. We'll talk about fields later because it's a relatively new idea in the world of physics. It's something that Einstein and a few others started pioneering. But some of the guys early on, like Faraday, lacked the mathematical ability to explain how a field would work. So it was kind of, taboo for a little while. It was something that sounded pretty, but we didn't have the math to back it up. So anyways, action at a distance forces. This is gravity. Gravity is the most popular example of an action at a distance force, right? The moon does not need to be in contact with the Earth, but the moon experiences the force of gravity that the Earth generates, and that's why the moon stays in orbit around the planet. You are experiencing a force of gravity exerted by the planet, and you are moving towards the center of the planet. Right now, you're sitting on a very large shelf, preventing you from falling any further, but just like any other shelf, a shelf on a wall, if you've got a picture frame up there, then remove the shelf and it's going to fall. It's going to fall down to the next thing that's going to prevent it from moving. And so gravity doesn't need to make contact, right? You don't need to have the Earth and the moon in physical contact for that force to be felt. This is what a force at a distance really comes down to. We will always use for the gravitational force F with the subscript of a G. So I'll say F sub G is your weight. It is the force of gravity acting on an object. It is going to be something that we're going to include in a lot of our calculations. So gravitational forces on Earth. They are your weight. The book goes into the whole thing on weight, but we're not going to get to that. That's the symbols and the abbreviations that we're going to use. Free body diagrams are a great way of diagramming what forces are acting on an object, because there might not be only one force acting on an object. There could be multiple forces acting on an object. Some of them might cancel out. Some of them might work together. Some of them might have nothing to do with one another. Just like in projectiles, your horizontal and vertical directions are completely independent of one another. So if you've got two forces acting on something at right angles, then they have no interaction together. So the free body diagram is a representation of all of the known forces acting on an object. Everything you know about it, you can include in your free body diagram. And that's what we're going to practice drawing right now. So you'll see a couple of examples. Now, you've got to label these arrows. If you don't label these arrows, then what you draw isn't going to make any sense to you when you go back to read the problem to try and figure out what's going on with it. So our first example, right? Your thought process for all of these are going to be the same. We need to draw a representation of this object. So there's my ball falling freely downward through the air, just like all of our old drop problems. What force is causing that object to fall? What force is causing that object to move? It is the force of gravity. And in what direction does the force of gravity always act? It always acts in that downward direction. Fantastic. Now, are there any other forces acting on this object in real life? Well, yeah, absolutely, right? We don't exist in that massive vacuum chamber that the video I showed you guys for the bowling ball and feather had, right? It removed all of the air at that NASA testing facility. That doesn't exist, so there is some air resistance. Now, I want you to notice that the size of these two arrows are not the same. Right? The force of air resistance is going to be a little bit less than the force of gravity, which is why objects accelerate downward towards the ground. But that was our first example. That's it, right? Just label the forces that are acting on the object. We have a book being pushed to the right across the table. Again, draw a representation of the object. There's my book. Not a very good looking book, right? Not something I want to read, but it's there. It doesn't have to be a fantastic piece of artwork that you submit for your free body diagrams. What force is causing the object to move to the right? This is going to be your applied force, right? It's a very generic way of describing, hey, I'm pushing it to the right. This is my applied force. I'm going to label it as FA. There are other forces acting on this object, right? There's the force of friction, always going to be present, attempting to slow it down, attempting maybe to prevent you from moving it, those sorts of things. So friction always acts opposite the motion or the attempted motion. Those are also not the only two forces acting on the object. Those are the only two acting in the left and right direction. But remember, we're on Earth. Gravity. Gravity is always going to be a thing. And if gravity is a thing, look at the vectors that we have right here. Those are not balanced out. Those are not canceled out, right? FA and FF, your applied force and your force of friction, could cancel each other out and work against one another, but there's nothing canceling out the weight of this object, the force of gravity acting on this object. So it should be falling through the table. Well, if it's not falling through the table, then that means the table had to apply a force to prevent the book from moving through the table. And again, that is coming from the intermolecular forces that make up the table, right? The cells in the wood or whatever it might have been, whatever kind of table it is you're using. The atoms in the marble, whatever it might be. If you've got, marble, granite, probably not marble. I've got granite countertops. I think they're actually quartz. Doesn't matter, right? You've got atoms in there. Doesn't matter what you're dealing with. I think the lab table here at school is granite. So, that's a solid, no cells, but you get the idea. Those are the forces acting on the object. There are relationships that we're going to talk about with those different kinds of forces. More often than not, your free body diagrams are going to look a lot like this. Now, if we wanted to add up the net forces acting on the object, we have to find all of the vertical and horizontal components, add them up, and then find the resultant between them. So in this particular case, a book is being pushed across the table with a force of 5 newtons to the right. 2 newtons is the force of friction. And then I've got a weight of 10 newtons and a normal force being applied of 10 newtons. So it's the same free body diagram that we just had. All you're doing is adding numbers to it, right? And these numbers will show you direction and things like that that are really, really important. And we should be able to notice just off the bat from looking at this that your vertical direction is completely canceled out. This book is sitting on the table, not falling through the table or being thrown up into the air. So those two should be equal and opposite. You'll also notice that you probably need to give one of them a negative value so that they do indeed cancel out. And we'll talk about that more in a moment. Your net force is your sum of all of the forces you have on the acting on the object, right? So horizontally, left and right, my net force moving left and right would be my applied force plus my force of friction. And notice, though, that we have to take into account direction. Now, I could have made my applied force going to the right a negative, but in normal coordinate systems, going to the right is always going to be a positive value, and going to the left was always a negative. So that's what I used. But it really doesn't matter as long as they have the opposite sign. If you described the applied force direction as negative, then your answer would be a -3. But the fact that they have the same sign would tell you what direction they were going in. And then your vertical forces, yet again, the same thing, right? Weight should be a negative force because gravity is always pulling things down towards the planet. We'll do more practice with this, obviously, but I want you to notice how we found the net vertical force to be 0. So your net force acting on the object is 3 newtons to the right, and that is why it accelerates to the right. That was it. That was your overview of free body diagrams and how we diagram and label these force vectors.